Hello, I'm Robert Sawart, and this is my personal analysis and interpretation of the Erlang programming language. To understand Erlang, you must first understand functional programming languages. At the basic level, functional programs evaluate expressions, where imperative programs are a collection of statements. Another distinction between the two is functional programs don't have subroutines. Imperative languages utilize functions as subroutines, which contain another set of statements separate from the main code block. Functional languages use identifiers, literals, and operators, including arithmetic and Boolean, to generate expressions. Functional environments generally avoid a mutable state. This means the state never changes. Just like the environment state, data values never change, only new data is processed. Compared to other languages, once a functional variable is declared, it may never change for the remainder of its life. Erlang was developed by Ericsson Computer Science Laboratory in 1986. After it found success with multi-core processing, it was released to the public openly in the year 2000. Ericsson created this language to develop fault-tolerant, distributable, real-time operational applications. Erlang has its own database, Mnesia, which uses arbitrary data structures. These tables do not represent a traditional n-by-n table structure. Erlang is used in many companies today. Amazon uses Erlang to implement SimpleDB and provides database services as a part of the Amazon Elastic Compute Cloud. Yahoo uses Erlang in its social bookmarking service, Delicious, which has more than 5 million users and 150 million bookmark URLs. Facebook uses Erlang to power the back end of its chat service, handling more than 100 million active users. T-Mobile uses Erlang in its SMS and authentication systems, while Motorola uses it in call processing products in the public safety industry. The diagram on the right shows Lime, a web hosting service, its structure which utilizes both Erlang and Mnesia. Erlang isn't suitable for all programming situations, but then again, no language ever is. I would recommend anyone who wants a number crunching application, graphic intensive program, or mobile system to avoid Erlang. Instead, I would recommend Erlang to be used for large-scale messaging systems and large arbitrary data storage. These systems would be expected to run at all hours of the day with little to no downtime. This means an upgrade of this system would not affect the user end at all. With a design of failure detection and replication, an Erlang-powered system would be practically indestructible. So why learn Erlang? I believe a programmer should learn Erlang if they want a deeper understanding of functional programming languages. I recommend Erlang if you want to develop programs that run fast on multi-core computers, you want fault-tolerant, modifiable applications, you have a general interest in functional programming techniques, you want a language with experience in large-scale real industrial products, and you want to type minimal lines of code. Ericsson designed the language to run independent of the operating system, and this created the obstacle of communicating to foreign devices and languages. To adjust, Erlang was created to communicate solely through input and output devices. This design feature meant foreign software and hardware failures have no detriment to the Erlang environment. This way, the language communicates through these devices and to itself through messages and pattern matching. Using messages and pattern matching, Erlang is used to develop systems with failure detection and replication. In my personal opinion, failure detection and replication is the most beneficial aspect of using Erlang to develop software systems. With distributed systems, companies generally want them up and running at all hours of the day. With failure detection, a system will never show fault to the user, and when a fault is discovered, it adjusts properly without negatively affecting the user's usability. Replication is important also because machine or hardware failure can cause an Erlang environment to fail completely. In situations such as this, there are multiple identical machines and systems running side by side that notice when other systems crash and will resume control of software processes. While the second system is now the leading controller of the environment, all other replications are updated to replicate the newer functioning system. The highest nodes or processes in the hierarchy contain precise definitions on what to do when a process fails. To adjust for the failure, these processes have the ability to create new processes that adjust for known failure. Lower level processes in the structure perform computations to handle the replication. I personally picture the structure to resemble a two-layered cake with a chocolate layer on the bottom and a vanilla layer on top, with icing spread all around the outside and in between the two layers. For those with a lack of imagination, this may clear up the picture. You can think of the chocolate layer as the layer of processes that handle all the computations of the system. The vanilla layer handles the replication. The icing is the supervising processes that govern all other processes and send messages throughout the system with instructions on what to do. Developing Erlang systems is not as easy as it may sound, and it's definitely not magic. Designing these systems take time and careful preparation in design. The purpose of the replication idea was best explained by designer Joe Armstrong. The probability of one machine failing is more likely than the probability of multiple systems failing. This means a system's probability of success increases when it contains multiple identical isolated machines. Erlang was implemented in Prolog, and as such, the language inherited Prolog syntax. This includes variables, atoms, tuples, and lists. Expressions are created by a proper grouping of these elements, and the overall structure of the program is only seen in its design. Compared to imperative languages such as Java that contain variables, keywords, and literals and identifiers to form code blocks. The overall structure of those programs can often be seen visually when looking at the code itself. The Erlang program on the right is a structure of how general Erlang programs look. The Java structure on the left is how most imperative languages are structured. As you can see, the functions do not replicate each other in any sort. Erlang is available online on their website and can be installed onto Mac and Windows operating systems. Once the shell is open, users are prompted with the following text. The first few lines provide information about the shell, and the last line is the shell waiting for the user input. Text editing in Erlang can be done in these following ways. The caret represents the control key, and the letter corresponds to the key combination. For instance, Control P fetches the previous line, Control N fetches the next line. Control A places the cursor at the beginning of the current line, while Control E places the cursor at the end of the line. Control F moves the cursor forward one character, and Control B moves it backward one character. Control D deletes the current character under the cursor, and return evaluates the current expression on the line. Arithmetic expressions follow the order of operations as expected. This order can be altered by grouping smaller expressions inside parentheses. Data types do not need to be declared for variable usage or expression. All expressions end with a dot. Variables must start with uppercase letters. On the first line, you can see I entered an expression, and the second line, or the line underneath, is a returned value. The second line I declared the variable x to equal 24, and in the third line I used the same expression, except I substituted the integer 24 with the variable x. Atoms represent non-numerical constant values. These are global. Atoms start with lowercase letters and contain alphanumeric characters, including underscores and @ symbols. A few lines 14, 15, and 60 example the different ways to initialize atoms. Tuples are groups of elements into a single entity. These are similar to arrays. These can be created by enclosing individual elements inside curly brackets. Elements are separated by commas, and they contain any Erlang element. Line 1 examples an Erlang tuple, and the second line is the return value of the tuple stored in the variable student. As said earlier, Erlang uses messages for communication throughout its system. Pattern matching selects what messages and which information inside the message is important. Many processes may read the same message but never read the same information. Line 2 takes the tuple from line 1 and finds the name Robert and assigns it to the variable who. Line 3 returns the variable. Lists are similar to tuples and may contain a variety of elements. These are created by grouping elements inside square brackets instead of curly brackets, and are organized or can be random. Line 4 is a shopping list that I created with items and the quantities to purchase. Line 5 is a random list, exempling that no structure is necessary when creating these lists. By combining these simple basics, programmers create robust systems. These are upgradable without downtime, automatic replication occurs, they have failure correction, large data storage, and minimal memory usage. These 5 points are what make Erlang an awesome idea to use when building complex and robust software systems. Thank you for reviewing my presentation, and I hope it was informative and you enjoyed it. These are my references.